Good morning. Thank you for attending this presentation. I'm Vincent Kelleher. I'm a software engineer at the Gaia-X CTO team. So I'm pleased to present the Gaia-X Ontology, the service offering encyclopedia. To give you some context, I'm not an ontology expert, and I won't claim to be. There are some in this room. I'm more on the tech side. In this presentation, I'll try to explain the basics of an ontology, seen by a tech guy. I'll show you how we can visualize, serialize them, how the Gaia-X ontology is built, how it's broadcasted, and EIY, how to extend it yourself. It's a pretty lightweight presentation. If you have any questions during the presentation, just raise your hand. It'll be a pleasure to answer any question you could have. So first of all, I'll start by presenting ontologies by reading this definition from ontotext.com. So an ontology is a formal description of knowledge as a set of concepts within a domain and the relationships that hold between them. Almost every word in this definition is important in the ontology world, may it be knowledge, concepts, relationships. Ontologies are very appreciated in the artificial intelligence domain. To start, they allow everybody to communicate with the same vocabulary. They define a context in a way. They allow to describe the world around you. If we do an analogy with object-oriented programming, which is the domain from which I come from, you'll see that ontologists and developers like to describe what they see, describe what they're manipulating, and once the whole vocabulary is set up, you can really use it in a natural way. A well-built ontology is going to be like a well-built code, class, data structure. It's going to improve problem solving. It's also going to improve problem solving because everybody is going to have a common ground for communicating and for the vocabulary that's going to be used. So it also improves communication. In the Gaia-X ecosystem, and in almost every ecosystem, it acts as a single point of truth. An ontology, from my point of view, won't need to exist if you have only one person using it. An ontology is made to be shared. It's made to be extended. It's made to be reused, to be linked with other ontologies. So it's really a vocabulary we're going to use to discuss with other people, to discuss with machines for exchanges and interactions. An ontology is ideal for building knowledge graphs and semantic graphs and semantic networks, whatever you want to call them. They allow to, as the description was given before the definition, they allow to link concepts together, and they allow you to navigate in a knowledge graph. They're a great base for semantic reasoning, for what we can call inference as well. You're going to have a set of known facts, knowledge that you have, and with that knowledge and these elements, you're going to be able to infer new facts from them. For example, you're going to be in the Gaia-X context. You're going to describe your service offering. You're going to describe your data centers, the resources they have, what CPU they run on, where they're located. And from that, I'll be able to tell you, okay, you want to have a service that's only hosted in an English-speaking country. I can just go through the knowledge graph, get the location of the data centers, and just check out the country and see, okay, it's English speaking, you can host it here. So from known facts, I can infer new knowledge. Also, for the ontology geeks, people that really go far in ontologies, you can apply set theory. my mathematics teacher would tell me to stay away from that because I'm not good at maths. So I'm not going to go into that, but you can go into unions, intersections, differences. You can do a lot of manipulations which will allow you to categorize data and knowledge. Now that I've defined an ontology, I've tried to define an ontology as I'm not an expert. I'm going to show you how you can visualize them, how you can describe them in a machine language. So ontologies can be visualized as RDFS. RDFS is Resource Description Framework Schema. If we have to compare to object-oriented programming, RDFS will define the classes, the attributes, and RDF is going to describe the instances. You're going to have a class like a car, for example. That's RDFS. You're describing it. Soon as you go into new car or instantiate it, you're in the RDF world. So these graphs, each class, is going to be a node. Each relationship is going to be an edge. Pretty simple. And also, before I forget, RDFS is a semantic extension of RDF. That's the basics. Subject, predicate, object. That's how we're going to build a whole ontology graph. I hope nobody's hungry in this room. I'm going to show you the pizza ontology, which is, I reassure you, I didn't build that during my free time. That's not my usual leisure. It's an ontology that's used to promote ontologies that has been defined, I think, in 2014 or a bit before. It has been used in Protégé and all other solutions to present what's an ontology and how it can be used. This ontology is going to describe the whole pizza domain in a way. I think everybody knows what a pizza is here, so we'll be on common ground. For example, you can explain what a topping is. You've got pizza toppings, you've got the subclasses. So as I was saying, you've got the subject, predicate, and object. You can have also named pizzas, all the famous pizzas like margarita, everything. They all are part of the named pizza class. You can see that the toppings, you can say that, for example, a margarita has a tomato topping or a mozzarella topping. So everything there describes a pizza from spiciness, topping, and whatever. With this graph, I could build a revolutionary system that could find any pizza for you, given your preferences. So by navigating this graph, I can tell you, okay, you want a pizza that's a bit spicy with tomato or whatever. I can infer it, go through the graph, navigate to find what you're looking for. So it's really useful to have these visualizations to understand as humans and really navigate the whole thing visually. But in our case, we're discussing with machines. There are exchanges happening with machines. So we can also serialize these RDF and RDFS graphs. Yep.
Actually, a question, you made the analogy with the object-oriented work, and that you have classes, when you have classes, you're in RDFS.
Yep.
And when you have instances, you're in RDF.
Yep.
And for those pizza, I would say like the margarita should be an instance. So are we still in the RDFS world, or is it like a mix of RDF and RDFS?
We're still in the RDFS world because we're describing a type of pizza. You could have a factory that's building margaritas with just an instantiation, new margarita, and it's really a given type in this case. Thank you. So as I was saying, we can serialize these RDF graphs to make them understandable by machines, make them parsable and shareable, because a JPEG image is maybe a bit big to send. So that's where we use all ontologies. For example, it's a format which has different syntaxes, so serializations. You can have them in RDF XML, you can have them in Turtle, Manchester syntax, OWL XML, you can have really multiple syntaxes. And there are other ontology languages that exist, but I won't go into these. So we move from our subject, predicate, object, image, graph, to something that looks like this when we're using Turtle, for example. So you see it's still a pretty simple visualization. We can have this in XML, and we can serialize them the way we want. Every element here has the same semantical value. That is important. Whatever the shape, whatever the format, they still mean the same thing. So for example, if we take our name pizzas, I'm going to say, okay, I'd like to describe it with Turtle. And that's RDF. So when you start describing it, you can see that, for example, I'm going to describe the has topping property, object property that's going to be here with the inverse, etc. You're going to have the tomato topping, mozzarella. We can see that I defined the name pizza. And you can see that the margarita here, that has the mozzarella topping and everything, is described at the bottom. They have the same semantic value, whether it's an image or it's a text. Also, I could move to RDF XML serialization. That has the same semantic value as what I showed previously. So I think you get the way it works. Okay, so any questions up to now? Perfect. So now we're going to move on to really the Gaia-X ecosystem and how we build it. So first of all, the ontology is the business of the service characteristics working group. Awesome community. I see some of you are from the working group in this audience. It's composed of experts, ontology experts, infrastructure experts, people that really have a detailed understanding of how ontologies work and how infrastructure, data resources, and all these elements work. They're the best people you could find to describe everything, and they've done a massive job in the last year or two to build an ontology that has now more than 50 classes and really intricate elements within it. They describe this ontology using LinkML, which is a linked data modeling language. It's mostly endorsed by the Berkeley University. They have a lot of people that work on biomodels, a lot of things that my simple brain cannot cope with. So I'm just gonna talk about it easily. There are renowned experts everywhere in the field of ontologies. So if ever you have the luck of working with people like that, they're really wise people. The Gaia-X lab team actively contributes to LinkML. It's a tool that's entirely open source, that has an awesome community that's really very open to contribution. They like having biomodel experts, they like having developers, they have architects, they have everybody in the community, and everybody brings something to the community. So at the Gaia-X lab team, we really enjoy contributing to that project, as open source is as well part of our motto. LinkML is entirely based on YAML files. You're going to have one input YAML file where you're going to describe your ontology, describe all the elements, and then the power of LinkML resides in the generators. You have generators for almost anything you can need. Python, TypeScript, OWL, Shackle, you name it, they have it. They can even produce documentation and interactive documentation for you, as you'll see in the later slides. In the case of the Gaia-X Ontology, the generation is done through our GitLab CI on the ontology repository. Quick LinkML file, basic. I'm still in pizzas. You'll see I'm a monomaniac when I start. We've got the prefixes, as you could see in the usual semantic graph in a way. We can define slots, which are the attributes of classes. You've got classes, which are just like object-oriented programming, abstract classes. You also have mixins. Please note that LinkML has single inheritance, so a class can inherit another one, but you can also inherit in a way multiple classes through mixins. They're like interfaces, we're going to say, in object-oriented programming. Okay, so you see there's a pipeline on the image. We're going into the GitLab CI pipeline. We have all these LinkML files. These LinkML files are going to be used to generate these outputs with 3 different generators. First one, the JSON-LD context generator. So JSON-LD context, they give semantical meaning to JSON-LD files. They describe the common Gaia-X vocabulary. When you have a discussion between human beings, if I go in the street, if I go to a C-level meeting in any big corporation, if I start talking about a VP, they're going to say, okay, vice president, no issue. No, I was talking about a verifiable presentation. JSON-LD context, they allow you to give the context of the discussion, in a way, the machine discussion. So when you're in a Gaia-X context, when I talk about a data center, when I talk about a resource, I'm going to describe precisely what it means in the Gaia-X ecosystem. So all the machines and the humans that are discussing together can have the same common knowledge. Then we generate shackle shapes. Shackle is a W3C standard. It's a format that defines the conditions and that ensures that an RDF graph is valid through what they call shapes. You're going to describe the shape in a way of all the attributes you want, the cardinalities, the types of data, and your RDF graph has to go into that shape in a way, has to fit into the shape. So it's really a validation system format. And then we have OWL ontologies, which is a semantic web language, which is used to represent things, group of things, and the relations within ontologies. That's what I showed you previously in the text examples. So this is the part where I add some added value in the service characteristics working group. All the awesome folks from the working group built the ontology. It was there, it was just waiting to be published and built and tested and broadcasted. So it's also had tests, which we improved a bit in the last year. So you have to know that each entity that's described in the ontology is tested in the context of the Gaia-X compliance. You cannot imagine the importance that the service characteristic working group has in the way the compliance works. If they describe something incorrectly, if they make a modification, it can blow up the whole compliance now, because we're entirely correlated and linked to what they're doing. So that's why there are tests that exist. We use TypeScript with vtest, which is a test framework. And every deliverable I showed you before, JSON-LD context, shackle shapes, and OWL ontologies, they're used to run these tests in true compliance conditions. We use the same components as the ones in the compliance. We use the JSON-LD context to give the semantic meaning to the JSON-LD data files we use. The OWL ontologies will give the class hierarchy, and the shackle shapes are finally used to just test the shapes, just like the compliance. Once you describe an entity in the ontology, you're going to build a JSON-LD test data file, one that's going to be valid. Okay, I'm going to describe my data center with all the racks, what is the energy consumption, everything. Give all the good formats, but you're going to also do test cases that don't pass. You're going to describe, I don't know, the energy consumption in liters. You're going to try all different things to say, okay, the shackle shapes are working correctly and everything's working correctly. So once we deliver these 3 deliverables, we know that they're fine and that they work together in a compliance environment. Are there any questions at the moment? Perfect. Moving on. We have our deliverables. That's great. We're happy. Now we have to broadcast them. So that's where the magic happens. We have NPM that's used, but I'm going to set that one aside as it's not used for end users at the moment. It's just a proof of concept. Everything happens on the IPFS part. IPFS, Interplanetary File System. It's a decentralized file storage system. What happens is we pin, it's called pinning, the deliverables on the IPFS network. Then the Gaia-X registry collects these deliverables and exposes them as REST endpoints, which I will describe later on. These REST endpoints can be called by anybody. It's our single point of truth. And then we use the W3C Perma ID project, which is used to normalize endpoints and URLs in the semantic web context. To make it simple for the techies that are here, it's just an Apache HTTPD with .htaccess files that you can modify on a GitLab repo, on a GitHub repo. So it's pretty simple. And that's the way we build the deliverables. The IPFS parts, some people are going to say, why don't you publish them directly to a file system? Why are you decentralizing everything? IPFS is going to play a big role in the future versions of Gaia-X. As you probably heard in all the presentations, we want everything to be decentralized. We want the association to not be responsible of running anything. We want the ecosystem to be self-standing and working in a decentralized manner. So that's why we use IPFS at the moment. There's a principle that we're aiming for in the service characteristics working group. It's the FAIR principle. The data has to be findable. So that means that the metadata and data should be easily findable. That's something that's done through the documentation we build, through the endpoints that are easily understandable by humans. It has to be accessible, so it means we have to use open and free protocols. So HTTP is massively used. IPFS is not massively used, or not too much. Sorry, I have an IPFS fan here. It can be used by anybody. We use DNS with it, so anybody can collect it through IPFS if they want, if they don't want the REST endpoints. It has to be interoperable, so that's why we use languages such as OWL, Shackle, they're all open standards. And it has to be reusable. So everything has to be documented and has to be open to be reused and linked in other ontologies. If you want the Gaia-X Ontology documentation, on mobile it's not the best experience, but it works. You can have a look at it. All the classes are defined. You have the link to the repository that's in that documentation. So don't hesitate to scan the QR code. So we're still in the broadcasting the ontology. So as I explained previously, we use Perma ID, which is w3id.org. That's the root of the domain. We use the MIME types to specify which resource you want. That's for technical interoperability between Shackle chips, JSON-LD, and when you reference the context. So we have a single endpoint, which is the one you can see up above. The version at the moment, there's only development, but in future versions, you'll be able to say which version of the Gaia-X ontology you want to use. And depending on the accepts HTTP header, you're going to have either shackle shapes if you give a text turtle, application, LD JSON if you want the JSON LD context, and so on. So that's the way you can resolve the different formats you're looking for. And we've got this little URL that exists too. What is it used for? It's used for LinkML. The FAIR principle, the first slides I showed you, all talk about reusing, extending, linking, and that's why we have this URL. LinkML out of the box supports extension mechanisms, so you can import other ontologies. That's why we use this format of URL, because we don't have too much space. They said it has to be like that in the documentation. This will give you a YAML file with the whole Gaia-X ontology in it in LinkML format. So that means you have the freedom to extend any entity you want in that ontology and define your own ontology through LinkML. We want to do that because we know that we use JSON LD context, we use the whole ontology shackle shapes, but maybe there are people that want to generate TypeScript or Python with it, or whatever they want. They can extend the ontology and generate the deliverables they want. They're free to do whatever they want with it. Here is a quick example to show you how powerful and easy it is. You just need, this is a LinkML file, as I showed you previously. You just need to add the prefix for the Gaia-X ontology, which you can see here, development LinkML. Import the types that we produce at Gaia-X. And now I've created my own legal person that extends with the is a legal person. So that means now you can describe your own legal person. You can extend it. For example, I was saying I was a monomaniac. I'm not lying. I can add to a legal person a critical attribute that Gaia-X needs. What is a legal person's favorite pizza? This is innovation. So you can just do whatever you want. It is open. You can take advantage of the awesome work that the Service Characteristics Working Group did. I think this embodies, not the pizza part, but this embodies the power of having a member-driven system. We aren't responsible of the Gaia-X ontology, the members are. We just give the means to broadcast it, and then the members can do what they want. They can extend it, they can do whatever they want. All that's left for me is to thank you and ask you, do you have any questions? Thank you. Yes?
Yes, I didn't pay attention, but why did you choose LinkML, not RDFS? I mean, RDFS, you said at the beginning, most ontology are described with RDFS.
Yes, I wasn't the person who chose LinkML because I arrived last year. It was already there. I've discussed with Pierre that worked extensively on that. And when you look at the deliverables that we produce, if we had to maintain each of the deliverables manually, so like you're gonna add, you're gonna add an address to the legal person, for example, you're gonna have to do it in Shackle, you're gonna have to do it in the whole ontology, in everything you produce, and it means that you need someone or multiple people that have the knowledge in all these formats to be able to maintain it. And you lose that single point of truth system. Thank you. Yes?
So I understood it. The main specific language is produced by LinkML is let's say, describing all possible ways to deliver VCs for the Gaia-X ecosystem. If I now would like to generate Gaia-X compliant persons, VCs for participants, VCs for service offerings, is there a workflow to use LinkML to also generate these tools for my specific ecosystem? Not
Yes.
only for the validation part, also for building my own tools.
Yes, the example I showed you previously, you're going to extend the Gaia-X ontology, describe your own elements. The only constraint is that you have to extend the Gaia-X ontology elements for the base types. For example, the legal person, for anything that's in the label levels, criterias and standard conformity. standard compliance, sorry. For each element that's necessary in that, you're going to have to either use the Gaia-X entity, or you're going to have to extend that Gaia-X entity if you want to use your own entity. That's the only constraint you have. Then if you want to go and describe more elements, you can just describe them. There'll be linked data. The compliance engine is going to ignore them because it doesn't support them, but your data can exist and it won't clash with anything. So that's the thing. We yet to have to test a real case scenario, because at the moment we don't have any members that extended the ontology. We didn't do extensive testing of ontology extensions. So we have to see how the context is going to be loaded, how the whole ontology is going to be loaded. But our shackle engine supports class hierarchies. So if you describe my legal entity, my legal person, for example, that extends legal person, our engine is going to be capable through all ontologies to say, okay, my legal person is a legal person, so I can consider it as such. Does that answer your question? Yes. Awesome. Any other question? Well, thank you, everyone. Yeah.
You said that we can infer knowledge
Yes.
from methodology.
Yeah.
Do you have context for tools for this? Because I guess we need some kind of querying on those ontologies.
Great question. You have Sparkle, which is a query language and a protocol. I'm not an expert on Sparkle. I've never really used it. So it will allow you to go through the knowledge graph. In the compliance, what we did, the choice we took, as you could see in Evan's previous presentation, we decided to load all the linked data graph into a memgraph database and use the memgraph query language, which allows us to collect data. It's really powerful. If people want to have a look at it, it's very interesting technology. So you can go through a knowledge graph with any knowledge graph, any graph, database, Neo4j or whatever you want, you'll be able to do it. You're welcome. Yes?
Yeah, I have a question about the development endpoints you mentioned.
Yes.
You mentioned that when we are querying the endpoints with different content types,
Yep.
then we get different contents, like the response is different. And isn't it against like the content negotiation approach of semantic web, which should just change the representation and not the content itself?
Well, it's going to be cowardly, but I'm going to hide behind the document we used to build that. There's a W3C document that's called Best Practice Recipes for Publishing RDF. It's long. If you want, I can send it to you. And it describes how to publish RDF documents. And MIME type is the way they go for it. To give you more context as well, you saw the prefixes I was discussing about in LinkML. You've got prefixes in RDF, in Turtle. You've got them everywhere, and it's the same prefix. So if you want to keep the semantic value in a way, you cannot have a different URL for a same prefix, because we're going to validate JSON-LD data files with Turtle, with Shackle, sorry. So it means that if the prefixes don't match, Shackle and JSON-LD won't be able to say, okay, it's the same element we're discussing about. So that's why we need to have a single URL, a single prefix, because when you expand the values, as Evan showed you previously, they won't have the same absolute URL. I see you're not really convinced. Yeah, if you want to discuss, don't hesitate. We can discuss after, even on Slack, on the community. Any other question? Okay, well, thank you very much for your time. I hope you enjoyed the end of this summit, and have a good day.